channel. This is Leo, and let's do some more Leetcode problems today. So this problem is called redundant connection. So in this problem, a tree is defined as an undirected graph that's connected and has no cycles. So we were given a graph that started as a tree with n nodes labeled from 1 to n, with one additional edge added. The added edge has two different vertices chosen from 1 to n, and was not an edge that already existed. The graph is represented as an array edges of length n, where edges I, AI, BI indicates that there is an edge between nodes AI and BI in the graph. Return an edge that can be removed, so that the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs last in the input. So basically we were given a graph and it was supposed to be a tree, but with a redundant connection. Take a look at the example here. So the input is 1, 2, which is this edge, and 1, 3, which is this edge, and 2, 3. And this forms a cycle, which is not a tree. So in this case, we're going to remove the edge between 2 and 3, since it was added last. And after removing this one, we can have a tree starting with the root 1. Okay, and let's take a look at the example 2. This is 1, 2, 1, 2, 3, 3, 4, 1, 4, and 1, 5. Obviously, we can see that 1, 4 is a redundant connection. So, how do we approach this problem? So it's pretty simple here, as stated here. The added edge has two different vertices chosen from 1 to n. That means we have some edges here, and it adds another edge here. So when we're trying to define there's a loop or there's a cycle in the graph, we can use DFS. If we reached something that is marked as visited, we immediately know that there is a cycle in this graph. Okay? So the way we're going to do this is we first construct this graph and we traverse from each node to see whether it has a cycle in the graph or not. If it has, we're going to remove that edge. Okay? So let's see how it works. So first, we're going to construct the graph. I'm going to use a map with integer and a list of integers, since one node can have multiple edges to different nodes. So I'm going to call it graph, new hash map. And what are we going to put in it? First, we're going to put in empty lists. So the n is less than 1,000. So we're going to put 1,000 lists there. So graph dot put if absent I with a new array list. Okay, so now we can start building the graph with the edges we have. So for integer array edges in edges, let's call the starting node U, which is edge 0, and the ending target node is V. Okay. In order to mark them as visited, we still need a hash set, which I can set up here, and I can call it scene. It should be a new hash set. And so let's take a look here. if we have 1, 2, if it doesn't form a cycle, I will put that into our graph. Okay, so cycle check here, and I'm gonna put them into the graph. So graph.getU, add v, and graph.get v.add u. Okay, so the cycle check. Let's say if we have a function called hasPath or hasCycle, whatever you want to call it, starting from u to v with this hash set, and with the graph, if there's a cycle in it, we're going to return this edge, since this will be the edge that is redundant. Okay. All right, looks like we got something that we want. And we're going to call the hasPath function recursively with all the with all the nodes until we find the final edge. Okay. Yeah. Now let's code it out. Oh, I think we missed a return statement. So here, since we're not going to return anything, we can throw an exception like assertion error. Okay, like that. All right, next, let's try a hasPath function. So the starting point, start and end, and hash set scene, and also the hash map graph. Okay. So what are we going to check? If the start equals to end, that means there has already been a path there. So we should return true because we found a path. Okay. So they're just connected. They're like one node. And second, yeah, I don't think there's anything left to do. So we can just add it to the visited hash set. In this case, we're just going to add the start point. And we're going to traverse through all of its neighbors. So for all the neighbors, we're going to get graph, get u. Oh, sorry, it should be start. Okay. So with everything, if the hash set already contains it, like if we go through all the way here, 1 to 2, and then we have already visited 2, means we went from here, so we don't go back. Therefore, we're just going to skip this. Okay, so if scene.contains neighbor, we're just going to continue. And if hasPath with neighbor and scene and the graph, we will return true. Okay, otherwise we will return false. Okay, so theoretically, if we have 1, 2, and they will not form a path, so we're going to put them into the graph. 2, 3 is okay, 3 to 4 is okay, 1 to 4, there will be a problem. So there will be a cycle here. So if we call this one hasPath 1 to 4, there will be something. Okay, there will be 1, 2, 3, 4, and 1, 4. So in this case, it will return true. Therefore, we'll return this edge. Okay, let's see how it works. Okay, I think it passed. And as for the complexities, we're going to traverse through all the nodes in this graph, right? So it should be at least ON. And with every node, in the worst case, we have to check all of its neighbors. In the worst case, it will be all connected to the first node. So it should be n squared. Okay. And as for the space complexity, I think we need a hash set and a graph. Okay, so the graph should be the size of the input. So it should be ON. Okay, let's see. All right, I think it passed. So thank you so much for watching. I'll see you in our next video.